Welcome to the Deep Dive. Today we're heading high up into the Andes Mountains in Chile.
Right up into the dry air.
Exactly. Because we're going to examine a piece of engineering that is, and I don't think this is an overstatement, completely redefining how we look at the night sky.
Oh, it's not an overstatement at all.
We're doing a deep dive into the source material on the LSST camera. It's the technological heart of the Vera C Rubin Observatory.
And it's probably the biggest game changer in ground-based astronomy we've seen this decade. This isn't just another big telescope. It's the largest digital camera ever built, period.
It's now fully operational, right? Our sources said the shutter officially opened in early 2026.
That's right. It's up and running.
You know, the sources had this nickname for it that really stuck with me. They called it the Devil's Eye.
It's a fitting name.
I think it comes from this almost supernatural ability it has to see into the darkest corners of the cosmos. So our mission today is to unpack this thing, its incredible scale, and the two huge cosmic mysteries it was built to solve.
And I think the best way to get your head around its power is with an analogy.
Let's hear it.
Okay, so just picture this. You're standing here on Earth.
Right.
This camera is so powerful, it could spot a golf ball sitting on the surface of the moon.
A golf ball on the moon.
That immediately tells you everything about the precision.
It's that combination of light-gathering power and raw resolution.
But let's also talk about the physical scale, because this isn't something you can, put on a tripod.
Not even close. The camera unit itself is the size of a small car, like a big sedan, and it weighs 3 metric tons.
Wow.
It's an absolute beast of an instrument built to capture the entire southern sky, not just once, but over and over again for a decade.
Okay, so let's get into those technical specs because the numbers are they're staggering, and we need to translate them. Let's start with resolution.
Right. The key number you need to know is 3.2 billion pixels.
That's 3.2 gigapixels.
Exactly. And for comparison, a really high-end professional camera you might buy today has, what, maybe 50 megapixels?
Right, if you're lucky. This is 64 times that resolution.
So what does that mean in practice, that density of data?
It means that to view just one full resolution picture from this camera, one single shot, you would need 1,500 high-definition 4K TV screens.
1,500.
All mounted together on a giant wall, just to see one snapshot without losing any detail.
That's incredible.
Yeah.
But the really unique thing about the Rubin Observatory isn't just the pixels, it's the field of view, right? Usually, telescopes have to trade one for the other.
That's the trade-off. You either get super high resolution on a tiny spot or you go wide and lose detail.
So how did they manage to get both? How do you see such a huge piece of the sky with that kind of detail?
Well, that's where the really complex engineering comes in. The secret isn't just the sensor itself, it's the optics in front of it.
Like the glasses it wears.
Exactly like that. It uses a massive 3-mirror system, but the key is a set of 3 huge corrector lenses. The biggest one is almost 5 feet wide. And those lenses are what take the light from that huge area of sky and focus it perfectly onto that 3.2 billion pixel plane without any distortion.
So you get a crystal clear image across a patch of sky the size of, what was it?
40 full moons.
40 full moons in a single shot. And this ability to see wide and fast isn't a bonus feature, it's the whole point. It's built for speed.
It is. If you think of something like the James Webb Space Telescope as a sniper.
Right, zooming in on one tiny target for days.
The Rubin Observatory is the wide field surveillance system. It's designed to take one of those massive pictures every 20 seconds. Just sweeps and shoots, sweeps and shoots.
Every 20 seconds. So in the time we've just been talking, it's already taken a dozen pictures, each covering that massive area. And that repetition is what enables the next big thing, turning the universe into a movie.
That's the revolutionary part. It completely changes how we do astronomy. The whole plan is for 10 years. For a decade, that camera will scan the entire southern hemisphere sky over and over and over.
And it does a full sweep every few nights.
Right. And when you pile up all those observations, you stop getting a photo album.
You get a time-lapse.
You get a 10-year-long movie of the universe. We're moving away from comparing a photo from 1980 to a photo from 2020. Now we can see things change in near real time.
But what kinds of things actually change that fast? We tend to think of cosmic events as happening over, millions of years.
A surprising amount happens very quickly. We're talking about so-called transient events, things that flare up and disappear.
Like what?
Think about a star getting too close to a black hole and being shredded apart, a tidal disruption event. That process is chaotic, and it changes on the scale of minutes and hours.
Wait, are you saying we could actually record a star being eaten by a black hole from start to finish?
We will see the process of that black hole feeding in real time. We'll also catch things like kilonovae, these insane explosions when two neutron stars merge.
Those are incredibly fast,
Yeah.
right? And violent.
Very. And catching them just minutes after they begin will tell us so much about how heavy elements like gold and platinum are made. Suddenly, the sky isn't this static, unchanging background anymore.
It becomes a living, dynamic thing.
Precisely.
That is just a phenomenal shift in perspective. But let's talk about why we spent billions to build this devil's eye. The mission is twofold: the invisible and the dangerous. Let's start with the invisible, dark matter.
Right. This is maybe the biggest mystery in all of cosmology.
Because 85% of all the mass in the universe is something we can't see.
Exactly. We call it dark matter. It doesn't emit light. It doesn't reflect light. It's totally invisible to a normal telescope.
But we know it's there because we can see its gravity pulling on everything, on galaxies and stars. So how does a camera that sees visible light map something that is fundamentally lightless?
It uses gravity itself as a kind of map maker. It's a principle called gravitational lensing. The camera is going to take pictures of billions of very distant galaxies. As the light from those galaxies travels towards us, it has to pass through this invisible web of dark matter that holds the universe together.
And the gravity from that invisible stuff bends the light, like looking through a distorted piece of glass or a funhouse mirror.
That's the perfect analogy. So when the LSST takes a picture of a billion galaxies, astronomers look for tiny, systematic distortions in their shapes.
A little stretch here, a slight curve there.
Right. And you can work backward from those distortions to figure out where the invisible mass is that must have caused the bending. The more galaxies you map, the clearer your picture of the universe's skeleton becomes.
And this isn't just about curiosity, is it? Creating a map like that tells us something fundamental.
It lets us test our most basic models of the universe. We can see if the dark matter is distributed the way our theories predict, if it's not. Well, if the map doesn't match the theory, it means we have to go back to the drawing board and fundamentally rethink how the universe began and how it grew.
That's the huge cosmic question. Now let's bring it back home. The second goal, the dangerous. We're talking about planetary defense.
This is where the camera becomes a planetary security system. The threat is very real. There are thousands of asteroids out there, near-Earth objects, that are big enough to wipe out a city.
And the problem has always been finding them all, especially the ones that are smaller or really dark and don't reflect much light.
Exactly. But the Rubin Observatory's whole design, that constant, wide, rapid sweep, is perfect for this. If an asteroid is moving, it will show up in one image.
And then in the next picture, 20 seconds later, it will have moved slightly.
And the software flags that movement instantly.
It's like a motion detector for the entire solar system, scanning constantly for anything that moves against background stars.
That's it. And the real power here is the lead time it gives us. We're not talking about finding an asteroid a year before it hits. Because this camera is so sensitive, it will spot these dangerous rocks years, maybe even decades, before they pose a threat.
And that gives us time to actually do something about it.
It gives governments and engineers the crucial window they need to plan a deflection mission or whatever other defense is necessary.
It's amazing that the same instrument mapping the invisible structure of the universe is also our early warning system for incoming rocks.
It's a beautiful link between fundamental science and, practical security.
Okay, so to recap, we have the incredible scale 3.2 gigapixels, the 40-moon field of view, and the dual mission of mapping dark matter and finding asteroids. But this whole project hinges on one final massive challenge: the data.
The data tsunami, as it's been called. When you build an instrument this fast, the output is just immense. Our sources confirmed it. Every single night, this observatory will generate 20 terabytes of raw data.
20 terabytes a night. That's just an unimaginable amount of information.
It is completely beyond human capacity to process. No team of astronomers, no matter how large, could possibly look through all of that data every night.
You'd never find anything. The subtle distortion of one galaxy, the tiny movement of one new asteroid, it would be lost.
It makes human review for the initial discovery phase totally obsolete.
But wait, if humans aren't looking at the raw data, doesn't that raise a problem? If we're relying entirely on automated systems to tell us what's important, how do we know we're not missing something unexpected, something the AI wasn't trained to look for?
That's an excellent and critical question, and it's why the project's success is completely dependent on very sophisticated AI. They're using machine learning in two key ways.
Okay, what are they?
The first is just classification. You train the AI to recognize all the known stuff stars, galaxies, nebulae, and filter it all out. That just gets rid of the noise.
So it clears the deck.
Right. But the second part is the real magic. Anomaly detection. This is AI that isn't trained on what the universe should look like. It's trained to spot anything that changes unexpectedly.
Anything that doesn't fit the pattern.
Exactly. A pixel that brightens when it shouldn't, an object that moves in a weird way. It flags those anomalies for the human astronomers to investigate. It lets them focus on the 2 or 3 aha moments that are hidden in those 20 terabytes every single night.
So for the first time, really, we're not just looking at the universe anymore. We're watching it happen. But we're relying on a machine to tell us where to look.
It's a complete paradigm shift. The human role changes from sifting through data to interpreting the most interesting bits that the AI finds.
Which leaves a pretty big question for you, the listener, to think about. If our biggest scientific discoveries are now coming from instruments that generate too much data for any person to see, and if AI is the essential guide telling us what's worth paying attention to, what does that mean for the future of discovery itself? Are we just seeing the universe through the filter of its code?
That is a profound thought.
Indeed it is. We've opened the devil's eye, and now we need an artificial brain to help us make sense of what it sees. Thank you for joining us for this deep dive. We'll catch you next time.